Okay, in section 1.5, what we're going to do is we're going to take a look at the geometry of solution sets. And in order to do that, we're first going to focus on a certain type of linear system called a homogeneous linear system. Now, a homogeneous linear system is just one in which every constant term is equal to 0. So you can see there's two examples of linear systems right below here. One of them's homogeneous and the other one's not. So the first one, you can just take a look, right? All the constant terms are equal to 0, so this one is homogeneous. And then for the second system here, you can just see that one of the constant terms is not equal to 0, and that's all it takes. As soon as one of the constant terms is not equal to 0, then that whole linear system is not homogeneous. Okay, a few comments that we'll make. What is the matrix equation of a homogeneous linear system? Well, remember you can compactly write linear systems in the form AX equals B, where A is your coefficient matrix, X is usually your variable matrix or your column of variables, and then B is your constant column, which is just a column vector consisting of all the constant terms. Well, if all the constant terms are equal to 0, then the column vector that is formed by putting them together is just going to be the 0 vector. So your constant column is really just the 0 vector. So we can just write the matrix equation as AX equals 0, and that's what you'll usually do. Another comment is that if you have a homogeneous linear system, you immediately have at least one solution without having to do any work. Let's look at this one, for example. If you wanted the general solution, you wouldn't be able to just look at that and just instantly see what the general solution is. Well, if you can, good for you, but I can't. But what you can do is immediately you can recognize that, hey, this system is homogeneous. That means if I set every variable equal to 0, it'll be true instantaneously, or it'll be satisfied instantaneously, right? Because if I set all the variables equal to 0, then the left-hand sides of each equation are going to be 0 automatically. So if the right-hand sides are equal to 0 as well, you know that's going to satisfy all the equations, setting all the variables to 0. So you immediately have one solution. Just take every variable equal to 0. That's called the trivial solution. Okay, that won't necessarily be the only solution. You might have other solutions, and if you do have other solutions, those other solutions are referred to as non-trivial solutions. So any solution where at least one of the variables is assigned a value other than 0, that's referred to as a non-trivial solution. And the third comment is that if you have a homogeneous linear system and you know, let's say you knew in advance that it had at least one non-trivial solution, that automatically tells you that it has infinitely many solutions. Because remember, a linear system either has no solution, a unique solution, or infinitely many solutions. So as soon as you have a non-trivial solution, you know you have the trivial solution as well. That means you have at least two solutions. And as soon as that's true, then you instantly know or can conclude that you have infinitely many solutions. Okay, and the last comment is just refers to when you're guaranteed to have infinitely many solutions, and that is if the linear system has a free variable, right? So if you write out the general solution and one of your variables requires a parameter, or more formally speaking, if you row reduce the augmented matrix and you've identified that you have at least one column in the coefficient matrix that's not a pivot column, well, then you know that you have a system that's going to have a free variable, which means that you're going to have infinitely many solutions. So having a homogeneous linear system, here's the upshot. If you have a homogeneous linear system, having infinitely many solutions is equivalent to having at least one free variable. That's all we're saying here for this last remark. Okay, so here's an example of a homogeneous linear system. How do you solve them? Well, so far, just solve them just like you would solve any other linear system, right? So let's write down the augmented matrix. We've got 1, negative 3, 2, 0. For the first row, 1, negative 2, 4, 0 for the second row, and then 1, 0, 8 for the third row. Okay, so one of the neat things with homogeneous linear systems is when you're doing row operations, you can just ignore the last column, right? Because no matter what row operations you do, adding or subtracting any multiples of any of these entries from each other, or multiplying any of them by any real numbers at all, or interchanging them, the result is always going to be the same. You're always just going to have zeros in your constant column. So when you're doing your row operations, here to get this into reduced or echelon form, so for example, we're going to take row 2, and subtract row 1, and then we're going to take row 3 and subtract row 1. I only need to do calculations in the coefficient matrix. I can right away, without doing any work, I can just copy down the constant column of all zeros, because none of the row operations is going to change that column. Okay, so the first row won't change. Now the second row, when we perform this subtraction, we're going to get 0, 1, 2. And then for our third row, we're going to have 0, 3, 6. Okay, and then now, so we can take row 1 and replace it with row 1 plus 3 row 2 to get rid of that negative 3. And then we'll take row 3 and we'll replace it with row 3 minus 3 row 2 to get rid of that 3. So we'll just clear out those two entries by doing this. Okay, let's see what happens. Yeah, I'll copy and paste here. So row 2 is not changing, but the other rows are. Okay, so we're adding row 2 to row 1 3 times. So you're going to get 1, 0, 8, 0. And then your third row, you're subtracting row 2 twice. You're just going to get a row of zeros here. Okay, and that is now in reduced row echelon form. So we're ready to write down the general solution. So column 3 is the only column that's not a pivot column, right? There's a leading 1 in columns 1 and columns 2, but column 3 doesn't have a pivot position. So the variable x3 is going to be assigned a parameter. Right? So let's give it a parameter s. Now for the second column, x2, well, that's a pivot column. So x2 is going to be a basic variable, so you can go write out the equation that corresponds to the pivot row in row 2. So you'll have x2 plus 2x3 is equal to 0. Solve that for x2. You get negative 2x3, or in other words, just negative 2s. Okay, so for the first row, or the first column, that's going to be another pivot column. So we'll write out the equation that corresponds to the pivot row. You've got x1 plus 8x3 is equal to 0. Okay, solve that for x1, and you're going to get negative 8x3, or in other words, negative 8s. Okay, so that gives us enough now to put together our general solution. Let's write it here. So x1, x2, x3, that's our variable vector. That's going to be equal to what? Let's put everything together. So we got minus 8s, minus 2s, and then s. And then normally we would just close this vector off and say where s is just an arbitrary real number. But instead we're going to take one more algebraic step here. We're going to pull the s out. Think of it as you're undoing the scalar multiplication here. So that we just have s, our parameter s, multiplied by one three-dimensional vector given by negative 8, negative 2, and positive 1. And then we'll say that is for arbitrary s in the reals. And by doing that, that's actually a specific form that we've chosen to write our solution in. Let me just write it as a comment up here. How about we use yellow? Well, so this is called parametric vector form. What we're doing essentially is we're writing all of our solutions as a multiple of a specific vector. Okay, so because every solution is just basically some real number s multiplied by that vector. In other words, the solution set for this linear system is just the set of all multiples of that one highlighted vector. So that's really what parametric vector form emphasizes.